Okay, so thanks a lot, Marco. So my first week here, but I'm enjoying it a lot and looking forward to the next two actually. So thanks a lot for the chance to talk here. Okay, so actually I decided to switch the order of these two topics. So I will start with the dark sectors and then go to the matter clustering. And maybe this reflects a little bit the two like sort of loves in my life. Well, I will not talk about the third love, which is more on the particle physics and the cosmology side. And but before that, let me just briefly flash the people behind here who did the actual work. So this is like not, I mean, at the moment the group in Munich is a little bit smaller because some people are actually moving out, some are moving in. And Enrique will also come later the week, I think. And what I'll be talking about is work from Enrique, Asma, the PhD student on the top left, and Dominic, student on the bottom here. Petter, I think, will also come. So he already, I mean, he was a student but left already a couple of years ago. And just to flash that, like Asma and also more particle physics postdoc Tobias will be also on the job market. Okay, so let's start, I thought, with this kind of slide that I stole here from Joachim Sorek, which is sort of a typical way to think about the landscape in particle physics, about searching for new physics, where we have somehow the energy scale, and we can be either at very high energies, and then we look for something that couples very strongly to the standard model, like at the colliders, or we can also be more in this kind of precision searches where we have a much lower energy scale, where in principle we understand the physics very precisely. So any new physics can only be a tiny effect, and we have to do really a precise analysis to find that. And so what you can see here on the y-axis is kind of the coupling to the standard model, because more or less by definition, what we are searching for sort of here in this particle physics world is something new that somehow modifies the standard model predictions. And as you know, there's basically no really robust evidence for any such new physics so far. So the standard model works very nicely. But of course, there is, in a sense, a very robust evidence for some kind of new physics that comes from the dark sector, the presence of dark energy and especially also dark matter. And so since we haven't really seen any impact sort of so far on this, on the standard model world, one can ask this question, like, could there be something going on specifically inside of this dark sector, and how could we actually hope to know about this? And so this is, of course, the question that we are discussing here in this workshop a lot. So this would be my version of this slide from before, now translated to this kind of dark sector world, where we replace the distance scale here from the kind of microscopic to the macroscopic scales. And we could now be looking for something that is not the coupling to the standard model, but that would be like the deviation from assuming a collisionless and cold dark matter as a description of this dark sector. No? So in principle, it could be that we have something that shows up on galactic scales, like kiloparsec scales, or even subgalactic scales, and modifies strongly the predictions of cold dark matter on that scales. Like, for example, self-interacting dark matter would be an example. But of course, this is highly nonlinear physics, so these small scales, so it's also not so easy to actually identify any deviation on these scales. So it's a bit like sort of the high energy frontier in particle physics. And we could also have the opposite side that we are mostly concerned here, where we are looking at really these very large length scales, where in principle we know that collisionless cold dark matter is like a good order zero sort of description. But still there could be actually some small deviations. And these are the ones that we could probe, of course, with the CMB and hopefully with the galaxy surveys. And I'll show some example here. So just to make this sketchy picture, of course, a little bit like to put it sort of here into these standard scales. This means that we, as in this precision low energy particle physics, we kind of need these two elements. So on the one hand, we need, of course, a very precise prediction within cold dark matter. So this is like zooming into this BAO part of the power spectrum in this plot. And like the width of this gray line should be sort of a plus minus 1% just variation. So this is what we would hope to predict at this level, hopefully, and measure. And the blue line would be an example for some interacting dark matter model that would give a slight deviation here. Okay, so as I said, I switched the order of these two topics I want to talk about. Basically, one is what could be the blue line, and the other one is sort of one approach that we are following to put this width of the gray line to be as small as possible. So I'll start with kind of this dark sector story. And so here I'll talk about some recent work together with Florian Niedermann and Martin Sloth, and involving also Enrique, who will come, I think, in week after next week. And it's also based on some projects from before involving Asma, the student. So she actually did a really great job interpolating from particle physics to cosmologies. She started like computing the dark matter drag opacity in thermal QFT for some interacting dark SUN sector. I'll come to that. And then went all the way actually to modify the SBT and DES pipeline to look for that particular model. So yeah, for me, like, just the question is there really something going on with dark matter? Can we test somehow or constrain how cold and collisionless it is already good enough, like as a motivation to address these kind of questions? But yeah, oftentimes people want to have some extra motivation. And so the one that we kind of took up here is, well, one of, let's say, the tensions we discussed about, of course, the most well-known one actually here. So for a second, as an excuse kind of to study this type of dark sector, I'll take the question about the Hubble tension, sort of pretend that it's really some beyond lambda CDM physics, and see whether this kind of particle physics modeling of the dark sector can help us there. And of course, this is all based on many, many works that are being done in this subject. So my take will be to try to start from something that is as close to kind of textbook particle physics as possible, and see how far we can get there. And of course, one standard way now, if you want to play this game, how you could change the value of H0 that you infer from CMB and BAO is to, as you know, change the prediction for the sound horizon in the theory model. And one standard way how one could achieve this is if there's some extra species around recombination that would do this job. And this is also the mechanism that, kind of this model I just want to present you will use. And so one very well studied possibility is to add some extra dark radiation into the energy budget of the universe that would do this job that I showed before. But it actually has kind of two problems. And one problem is that the amount of extra radiation you would need to add, so this is kind of the delta in effective versus the scale factor, around recombination, so this is the right part here of the diagram, would actually be in conflict with the bounds that we already have from BBN. And the second problem is that the kind of perturbations that you add by adding this extra dark radiation in the CMB do not match the measurement. So it's not only the sound horizon, of course. So basically just adding the extra radiation doesn't work really as a solution, as you know. And so this is where this kind of particle physics dark sector modeling sets in. What can we do about kind of solving these two problems? And so to follow this philosophy, the idea here is to, kind of go to the textbook and take the most sort of standard particle physics that we can think of, but now assume that this is kind of also going on in the dark sector, given that the standard model has all these particles, all these interactions. We could think maybe it's a little bit too simple to just take one non-interacting particle for dark matter. And one easy thing one could do is that one could think, well, in this dark sector, maybe there is some kind of gauge symmetry, like in the visible world, we know this exists, no? And so this would be the dark SUN, for example, as a non-abelian gauge group. And then another element from the standard model that we added here is a Higgs mechanism, so a spontaneous symmetry breaking. And so what does this help us here with this kind of problems of this extra radiation? So we have now a phase transition basically due to this dark Higgs from spontaneous symmetry breaking. So we assume this dark Higgs is in the fundamental of SUN. And then if it acquires a vacuum expectation value just in the standard Higgs book way, this would break the SUN spontaneously to SUN minus 1. And basically, if this is really just the standard textbook Lagrangian, if we are close to this kind of scale invariant situation, then this phase transition is basically supercooled. So you have a lot of latent heat that you then transfer into dark radiation. And so this means that you can nicely use this to basically start with an extremely cold temperature in your dark sector. And then from the phase transition, you convert the latent heat into radiation thermal energy that heats up the dark sector, so that basically you have a large sort of delta ineffective at late times during the recombination, but a very low delta ineffective during BBN. So you can, with this phase transition, basically solve this BBN bound problem of the extra radiation. Of course, it doesn't automatically solve also the problem that the CMB perturbations don't quite match the measurements. So you still have to kind of do something additional about the model. So what you can notice here is that basically this phase transition could take place more or less anywhere between BBN and recombination. So there's sort of many orders of magnitude. So you don't need to really tune the parameters too much to get it somewhere there. No? Mm-hmm. Mm-hmm. So the reason is that we, even after the symmetry breaking, we want to have some massless gauge bosons left because we still want to have some dark radiation. Otherwise, basically the gauge boson would just be massive and we wouldn't have any dark radiation left. Mm-hmm. Okay, so there will be some further features where this SUN like plays a role. No? This is a first order transition, and it is a super cooled phase transition if one is close to this kind of Coleman-Weinberg limit. Diego has also worked on this. No? Yeah. So this could be one of the things to look for. No? So you need a latent heat that basically gives you a delta ineffective, which is order 1 for this to work, right? No. Mm. It, it, it is somewhat small, but not that small, because at that time you don't have that many degrees of freedom anymore. So getting a delta n effective of 1 is adding a certain fraction, because otherwise it wouldn't also affect the expansion rate, right? So it's a smallish fraction, but not, it's basically the same fraction that you need to change Hubble by 7%, right? Okay, okay, let's wait. I'll show the plot in a few slides, okay? Okay, so first to address now this kind of second problem that just having the extra radiation actually gives you the wrong prediction for the CLs in the damping tail. So what we thought here is, if we follow this line of sort of just doing the most kind of textbook style physics in this dark sector, then, okay, we have a gauge field. We have that in the standard model. We have a Higgs field. We have that in the standard model. What about adding some fermions that are also transforming under this gauge symmetry? And so this would be this, what I already call dark matter. So due to the gauge symmetry, nicely, they are actually stable. So they are then a natural candidate for the dark matter. And so this will be this. So this is this version of this latest work that we looked at. So what consequence does this have? So basically, the nice thing about this is really you can just go to, the Lagrangian is like the vanilla Lagrangians here, right? So there's nothing really hard in the modeling you have to do. And so basically then, what kind of masses do we have in mind here? So we start sort of in the symmetric phase, and there we have basically some dark matter mass that we just assume to be heavy. Actually, the precise value will not really play a role, so that it's not really produced or destroyed in this phase transition. One could change this, but this is what we assume for now. And then, so once the phase transition happens, it basically gives a mass to the gauge bosons that correspond to the broken generators, of course. The SUN-1 gauge bosons stay massless. And there's also the Higgs mass, and in the Coleman-Weinberg setup is basically also fixed in terms of just the gauge coupling to be lighter by a factor of the gauge coupling than the gauge boson mass. So sort of the gauge coupling determines here the full hierarchy of mass scales. And then we can look at the dark matter. So now basically this n components of the dark matter, they would be split into one fundamental multiplet on the remaining SUN-1 from n-1 components, and one component which is neutral under this n-1. This is this what we call chi, the nth component, or chi0, because it's neutral. And so this is, of course, something that is very well known from electroweak symmetry breaking, that you will then get from these loops of the gauge bosons in the self-energy a different one-loop correction to the mass of the neutral and the charged component, like the Wiener mass splitting. And this mass splitting is actually also only sensitive to the VEF and the gauge coupling. So we basically have only the VEF and the gauge coupling really as relevant parameters, because it turns out that what matters for the cosmology is basically mostly this mass splitting then. So the neutral component is slightly lighter, and so now we can think about what this means for the cosmological history of that kind of dark sector. So, okay, this is a little bit of a busy plot, but we go through it step by step. So basically, we start on the left before the phase transition. So there, all the dark matter components are basically the same, and they interact with the gauge bosons, the non-abelian gauge bosons, and the Higgs interacts also with the non-abelian gauge bosons. So basically, the A mu and the psi, the Higgs and the gauge bosons, they form a self-interacting dark radiation that also self-interacts due to the non-abelian interaction. And then there is an interaction with the dark matter just from gauge interaction. So this is this kind of Compton scattering here, which is sort of the analog of baryon photon scattering. And the difference is that there is this kind of T-channel diagram due to the non-abelian vertex here, which actually changes the temperature scaling of that interaction rate. And this is something that people have exploited a lot already, that basically the interaction rate has the same redshift dependence as the Hubble rate for this kind of non-abelian case, so that this interaction stays relevant over a very long kind of cosmological epoch. Okay, so now on top we have the phase transition. So this splits the two components in the multiplet, but they can still actually talk to each other via these kind of conversion processes here, also with gauge bosons in the T-channel here. So they are actually also enhanced. So this keeps them actually in equilibrium with each other. So we still have essentially now, due to the supercooling, we produce dark radiation. So this is kind of the larger box. So we have more dark radiation after the phase transition, and it also still interacts with all of the dark matter effectively. Yeah. Right. Okay. Thanks for asking this. Yes, I should have mentioned this. So we assume basically, so this is sort of the philosophy here. So what can we tell about this dark sector, even if it doesn't really interact with our visible world? Yeah. So initially we have a very low temperature of this dark sector, much lower than the standard model. And now you can also ask the question, you can extrapolate to even earlier times, how could this have been initially produced? And this is sort of a very generic situation. If you have no equilibrium, you can have some kind of freeze-in production. If you produce sort of just like a little bit, let's say, of these dark sector particles, and they thermalize among themselves in this dark sector, you generically get this very cold initial dark sector. So we didn't include this here in the computation, but this is an obvious way how you can create this initial condition. Mm-hmm. The coupling to the standard model, we assume to be very small. The gauge coupling itself, yes. So to have basically to have this sort of separation of scales here, we have a gauge coupling itself that is much smaller than 1. So there's a certain range that works. Yeah. Mm-hmm. Mm-hmm. It is, yeah. Mm-hmm. Mm-hmm. So I mean, basically, yeah, there's a certain range of gauge couplings where we have the high enough interaction rate, and where we also get the tunneling rate. But essentially what helps a lot is that all this takes place after BBN. So compared to what you are usually sort of thinking about, now the Hubble rate is really much smaller, the universe is much older. So it's kind of easier with this very weak couplings to compete with this very small scale of the Hubble rate. So in a sense, we don't need a very strong coupling to already get some cosmologically relevant effects here, even with a gauge coupling of 0.1 or even smaller. The rate, for example, for the scattering processes is already above the Hubble rate. And we also do the standard computation of tunneling and so on. Okay, so then there's a step when basically the temperature reaches kind of the first sort of mass threshold, which is the mass of the Higgs particle. After the phase transition, so basically after the phase transition, the temperature of the dark sector reheats to something that is of the order of this G times V of the gauge boson mass, but slightly lower, so that they are not really produced after the phase transition. So the massive gauge bosons, they are already like away. But then at some point in the evolution, one hits this threshold of like the Higgs mass. So the Higgs drops out of the thermal plasma. This gives a little kind of boost on the dark radiation energy density, but turns out this is actually not so relevant. What is more relevant is then the next redshift here, where the temperature of this dark sector drops below the mass splitting, because then the thermal equilibrium between the charged and neutral states actually breaks down or prefers the kind of neutral component, so that this dark matter will now be predominantly going to the neutral component, to the lighter component, but this one doesn't interact with the remaining massless gauge bosons, so that effectively this interaction between dark matter and dark radiation basically freezes out. So it stops. No? And so then at some decoupling redshift, basically we are left with the self-interacting dark radiation and with dark matter, which from then on doesn't interact anymore. So this is basically the sketch of the evolution. So of course, what we did behind the scenes here is to work out the background evolution and the cosmic perturbations for this kind of setup using this interaction rate here. So I skip this here. You can ask me if you're interested, and I kind of go to the results. So adding this feature of this is where the name also comes from, this kind of dark radiation matter decoupling. What we find is that actually there is a very kind of peculiar sort of region here. So this is the upper panel are kind of the new parameters of the model. This is the delta ineffective, the decoupling redshift of this interaction, which we leave here sort of as a model parameter, but can map back to the gauge coupling if you like. Then what we also assume is that actually not all of the dark matter interacts here, but only a fraction, because otherwise this interaction would give a too strong actually suppression to the power spectrum to be viable. And we have some parameter for the interaction strength, which is basically not really constrained by the data, because it just tells us that it should be basically tightly coupled before the decoupling. So the most important parameter is this decoupling redshift. And if you look at the posterior here, this contours with the solid, like this filled contours, they are, I mean, what we call base combination. So this is basically a CMB plus a DZBAO plus a Pantheon plus. So no direct H0 information included. And still they have this kind of funny feature at a value of the decoupling redshift, which is somewhere between 1,000 and 10,000, where you see that you are basically having this kind of peak that gives you, allows with these data a higher value of the Hubble parameter. And so this is sort of a special, case where this decoupling happens somewhere actually not so far from the transition between radiation to matter domination, so radiation equality. And this is what the data seems to like most, where this interaction happening during radiation domination provides just enough suppression of the perturbations, but doesn't suppress the matter perturbations afterwards. So, I mean, Melissa Joseph, yeah. Yeah, yeah. We are trying right now, yeah. So, yeah, I mean, also SBT and ACT, this is what we look at right now. No? So for the moment, this is Planck CMB, what we look at there. No? So, but I should also say this, so, okay, I don't know what she was talking about precisely, but what I know from the papers, let's say, is that this feature also doesn't exist in these type of models where you have an extra radiation, or also in this kind of step models. But this is something that is really, somehow related to this extra feature of, I mean, there are also the versions where you assume that the dark radiation is interacting with the dark matter, but here on top, there is a kind of redshift dependent interaction, that stops at some point, right? And this is kind of what gives this, in the first place, somehow this solution. Mm-hmm. So this is the PLIC, I think. Yeah. Yeah. Mm-hmm. 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 Yeah. We are, yeah. I mean, like finding this motivates to look at this model more closely, I would say. So also this is kind of the textbook example of something that is affected by projection effects, no? Where you have this kind of long contour and then some particular value. So we thought we should maybe also do a profile likelihood. So just before that, just to flash these numbers here. So basically this would be an example of this, some of these tension metrics, right? So this, for example, this self-interacting dark radiation, even ignoring the BBN like problem, gives you something in these combinations that is like 3 sigma-ish. If you ask whether it can address the Hubble tension. And here, due to this feature, basically we go down to basically 1 point something sigma. So at this level of data combination, at least, it seems to really allow these large values. And whoops. Okay, so this is the profile likelihood. So on the left is basically the case where we have only this baseline data, so no shoes data, right? And it's profiled over age. And yeah, I mean, basically the green is just lambda CDM, and the black is the self-inducting dark radiation. And then we have this kind of dark radiation matter decoupling model where one sees that one can kind of, yeah, at 1 or 2 sigma go well into this kind of shoes band. And of course, if you combine it with shoes like on the right, then it massively prefers this large Hubble region, basically. Okay, we also looked a little bit at this kind of, I mean, since we discussed about tensions, so if we just look at the CMB kind of versus DESI sort of, which maybe isn't really a tension, but some people discuss sort of this consistency, right? So then on the right, I mean, in lambda CDM, so this is this omega m H naught RD plane, and kind of the DCDR2 here is the same sort of in both cases for these parameters, because you don't really change any of the late time physics in this model. And what changes is the CMB contour. So for lambda CDM, it is a little bit offset from DZ. As you know, this is from the DZ paper here, the right plot in lambda CDM. So if we try the same thing in this model, then we see that this kind of contour, I mean, we can go to a little bit lower omega m values, which then along this kind of geometric degeneracy line where you keep the angle to the CMB peak fixed, means that you also go a little bit to higher HRD. And the coloring shows that this happens actually for larger values of H. So basically, if you want to kind of go to larger Hubble, then you are sort of pushed also a little bit into this DZ region here in the omega m HRD plane. This is also something that has been observed a little bit in other models addressing the Hubble tension. And it happens basically in this model here as well. Maybe a little bit more strongly because it can go to these large H values without being too much excluded. So by the way, there's also the code here. So in case one wants to play with the model, one can do that. And okay, so this is the plot I was promising before. So, I mean, obviously ACT is probably going to have a word, something to say on this model. What is interesting is that there's also, due to this dark matter, dark radiation coupling, that then decouples. There is kind of a dark sound horizon, if you like, and a dark acoustic oscillation related to this dark sound horizon at this dark matter, dark radiation decoupling scale. So this would be something that to look for, of course, yeah, with DZ. Well, there could be then some further features that are basically not really required to, if you want to sort of play this Hubble tension game, but that would be also predicted by the model, which is some features of the phase transition. So I think you also had some talks the weeks before. There could be some kind of stochasticity generated in the phase transition. This would not really be, yeah, I mean, would actually not really show up in the CMB if the phase transition happens somewhere between BBN and somewhat before recombination, but could still be interesting if the phase transition moves more close sort of to the recombination era. The coupling is small, yeah. Mm-hmm. Is not very slow. It is more or less exponential because, yeah, in the temperature. No? Mm-hmm. Mm-hmm. Because of the, I mean, somehow the occupation of this mass splitted heavier and the lighter state goes kind of with a Boltzmann factor. No? And this drives the suppression of the interaction rate. No? Mm-hmm. But these kind of signatures related to the phase transition, they would not be related to this dark matter, dark radiation decoupling, but already the phase transition which happened before. No? So the phase transition and the, no. Mm-hmm. Pardon? The dark, they are, yes, exactly, they are. So, I mean, it is a bit similar, like, so, I mean, from this point of view, it's a bit similar, like the Saha equation and the normal recombination. So you basically get a dark sound horizon. But in your case, exponential decoupling, it works well. It works, I mean, to compute just the yes, yeah, it basically works well. No? I mean, at some point in the tail, of course, you always, I mean, the exponential, you cannot extrapolate to arbitrary scales, but as long as we can follow it, going below Hubble, it works well. Okay, then there was the third question already, like, I don't know, these gravitational waves are maybe for these very low energy or this kind of intermediate low energy phase transitions a bit on the tail. Yeah. So, I mean, this is basically fixed because if you want to be in this kind of high Hubble region, right? So then you see the decoupling redshift is at a couple of thousand. And so basically this more or less fixes this dark acoustic oscillation scale. So it is, I mean, like in megaparsec units where the BAO is sort of at 100, it is then maybe at, yeah, 88 or 85, something like this. Of course, with a smaller amplitude, because this is, yeah, kind of just a fraction of the dark matter that does these acoustic oscillations. Yeah, I mean, it is a okay, I mean, it is an acoustic oscillation, so in principle, yes. Yeah. but also suppressed somehow. Yeah. Mm. Yeah, I mean, the frequency of this, okay, now going back to the gravitational waves from the phase transition, the frequencies would be a little bit on the low side for these type of phase transitions that happen even after BBN. So one would be a bit on the tail in this kind of PTA regime here. So maybe not the first thing you would expect to see, but also not completely excluded here. Okay, since I promised to go also to the meta clustering, I want to go on, but we can have, yeah. Pardon? Mm-hmm. Yes, yeah. So, mm, yeah, I mean, here we just wanted to make sure that we are sort of not exceeding this kind of signal. So we didn't check, well, I mean, like maybe it's a bit too optimistic to actually explain kind of the nanograph with this type of transition. Yeah. Yeah. Mm-hmm. Yeah. So so basically this the phase transition happens at an energy scale where they cannot be really produced anymore. No? So before the phase transition, they are all massless, and then during the phase transition, or after the phase transition, basically the reheating is not high enough to really produce them. No? No? The dark matter here, the fermions, so there we assume this is actually much heavier. No? And for what we did here in this work is that we assume that it was already produced somewhere before, for example, we have this freeze-in. But of course, I mean, there's a lot of interest in like also producing these kind of particles during phase transitions. So if the mass scale is a bit comparable like to this phase transition scale, this could be also an interesting possibility actually. To pardon? Yeah, so this would be I mean, this is kind of sort of yeah, I mean, this would be very complementary thing. I mean, in principle, it's enough if there is kind of a gut scale particle that connects the two sectors, you would get a temperature of this dark sector that is sufficient. Yeah? So um, I don't know, maybe some exotic processes, whatever, but yeah. 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 Mm-hmm. Yeah. Yeah, exactly. So this is exactly relevant here. So this basically makes the interaction continue until this decoupling occurs. Otherwise, if you, pardon? Right, but you have the mass splitting of the dark matter due to the symmetry breaking, and then you at some point go to the neutral state, right? And the neutral state doesn't have this T-channel interaction with the massless gauge bosons. No? No? Um, the decoupling of so the decoupling of, I mean, basically of the dark matter dark radiation scattering. This is what we keep in the model, and so the kinetic equilibrium should also break down not too long after this decoupling occurs. No? Yeah. Right. Yeah. Mm-hmm. Yeah. Okay, so maybe there's some confusion. So there's some no. So you are talking about kind of this dark matter temperature scale, right? So this is the energy. Yeah. 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 Okay, so this is on the level of the perturbations, while the kinetic decoupling is kind of you need to wait with the energy transfer, right? So this happens. Yeah, no, this happens earlier because you have kind of for the scattering you have the momentum transfer cross section, and for the kinetic, I mean the temperature, you have this kind of energy transfer cross section, right? And then there is then there is then there is the other question, like these are the conversions between these kind of neutral and heavier states, and they decouple slightly after this dark matter dark radiation decoupling occurs, so that they are still sort of in Saha equilibrium while the decoupling of the dark matter dark radiation occurs. Okay, gets a bit detailed. I mean, we can discuss if you want to. So the decoupling dark matter dark radiation is around matter radiation equality. Yeah. This is actually what the parameters tell us is preferred if you want to raise the Hubble parameter. It's kind of fixing sort of the perturbations in the right way. Okay, now not much time left for going to the second thing, so maybe I will just skip this and okay, maybe just very briefly go a little bit through some things in the second part, or we can also stop here as you. Okay, yeah. So maybe a little bit. Okay. So now basically changing topics, I yeah want to go to and basically here present to you some idea I was working on that is really connected to matter clustering. So in principle, sort of maybe one of the simpler things if you think about galaxies, but still, of course, underlies at the end any perturbation theory prediction. And okay, so somehow the name of the game is what is this kind of velocity dispersion term here in the Euler equation. And of course, as you know, standard perturbation theory means we have no dispersion. In the EFT, it's kind of the most agnostic with parameterizing it in the most general way that it can possibly look like. And so the idea of this approach I want to present, this VPT, is that is in principle also conceptually very simple idea that we say, okay, the standard dark matter should be behaving as a collisionless gas, not a fluid. Collisionless is very different from a fluid and from a perfect fluid in particular. So basically, the idea is to basically have a perturbative solution of the collisionless Boltzmann equation together with gravity. So this is just the Vlasov equation for the phase-space distribution function. So the starting point would be basically not the fluid, but this Vlasov equation coupled to gravity. And so then this is, of course, a 7-dimensional object, so a bit hard to treat. And so the idea is to expand it into its cumulants. Then, of course, we get back the density and velocity in the 0th and 1st cumulant, and the velocity dispersion tensor here in the 2nd cumulant. And then one can write this cumulant generating function here, with this kind of auxiliary vector L. And if you Taylor expand in this vector L, the coefficients will be actually all the cumulants of your phase-space distribution function. So the set of cumulants has the same information as the phase-space distribution function. And so then if you take the Vlasov equation and kind of multiply it with this exponential integrate over this generating, integrate over all the momentum modes with this vector L and then Taylor expand the equation that you get in L, you generate the coupled hierarchy of evolution equations for the cumulants just from the collisionless Boltzmann equation. And of course, the zeroth and first are just the continuity in Euler equation with a stress energy that has its own equation, which is this equation shown here. So this is the equation of motion for the dispersion tensor, which is then having its own nonlinear terms, and on the right-hand side is sourced kind of by the third cumulant. And then we have an equation for the third cumulant sourced by the fourth cumulant, and so on and so forth. So we get this usual coupled hierarchy. And basically, the idea is very straightforward that we're following here. We are just taking these equations, and then we say, okay, to solve them, we somehow have to truncate somewhere as usual. And so we check then by changing this cumulant, this truncation order, whether what we get is actually making sense. So maybe briefly why one would actually do that. So of course we know that basically on large scales, this kind of a perfect pressureless fluid approximation is sort of okay, but then we have all the shell crossing going on. So what this means is that in SPT, in practice, kind of the loops are actually more UV sensitive than the physical sensitivity to these small scales actually is. No? So most of kind of the EFT counter terms kind of correct for the mistake that you do using SPT, plus of course a small extra physical effect from the actual back reaction of these small scales. So the idea is that in VPT somehow, well, in general, sort of, I mean, in the full kind of theory in this sense, for collisionless cold dark matter, this UV sensitivity is much smaller. So there is a UV screening. Otherwise, basically, it would also be, I mean, very hard to do any n-body simulation if this was not the case, because you would always be dominated by very small scale Nyquist effects. This is not the case in practice. So the idea is to somehow exploit actually this UV insensitivity a little bit more in perturbation theory in the first place. So this is the idea of VPT starting from this kind of collisionless equations. But of course, there will also be some source of this small scale physics, so sort of the physical effect of these kind of UV modes. So this will show up actually in this approach by the fact that the dispersion tensor and all even higher cumulants can actually develop an average value. So you have on very small scales, shell crossings going on everywhere in a statistical way. And this basically generates sort of a background, an average of this dispersion tensor. So this is a really non-perturbative quantity that can be dominated really by these small scales, which one cannot somehow predict. But then once this average dispersion is somehow there, it will actually generate also perturbations of the stress tensor on also large scales, because this acts as a source term for these perturbations in the background of your density perturbation. So it generates also large scale perturbations in the dispersion and in the higher cumulants. And this is exactly what we are computing in this approach. Yeah. Mm-hmm. Yeah. Mm-hmm. Yes. Yes. So basically, it's the density and velocity perturbations themselves that source then together with this average dispersion, but this is scale independent. The average dispersion is just required to generate any velocity dispersions at all. No? But once you have any non-zero value of this average dispersion, the collisionless equations predict you to generate also perturbations in the dispersion from the existing density and velocity perturbations. So they are basically proportional to them. So they are on large scales, also perturbative small. Okay, so the idea is that this VPT somehow builds in this kind of UV screening, and therefore you would get something that is not as much affected by these small scales, but has sort of just the physical impact of these small scales. Yeah? Of course, you still need this kind of average dispersion here. Okay, we are still working on also going to the IST case. So the way how it works, just, okay, maybe I skip this a little bit, but just to show you very briefly. So we somehow look at this normalized dispersion tensor here, which is convenient, and then split it into the average, which due to just homogeneity isotropy is proportional to the unit 3×3 matrix. So we just have one function of time, basically. This is this epsilon of z, plus then the perturbations that are scale dependent and on large scales are going to be perturbative. So this average dispersion basically brings in a new scale into the problem compared to SPT. This is the main difference, which is this dispersion scale. And of course, this has been noticed before. The value of this dispersion scale is a little bit higher, but not too far actually from the nonlinear scale. So for this VPT, this is basically our non-perturbative input, this average dispersion, okay? Yeah. Mm-hmm. Mm-hmm. Yeah, so we have, let's see. We have basically, I mean, we have tried 3 different methods to determine it. I think I have it here. Whoop. So basically, one possibility is to, yeah. Mm-hmm. So the non-perturbative input is this average dispersion. The delta epsilon, this is what we compute then from the equation of motion, from the collisionless Vlasov equation, collisionless Boltzmann equation, right? Yeah, exactly. So what is the non-perturbative input is this epsilon of z, this average thing, which in a sense, if you like, gets contributions really from all scales, no? And in particular from small scales where the shell crossing happens. No? So this is where the shell crossing enters the whole game. No? But once you have this average dispersion, the equations predict you that you generate these perturbations in epsilon. No? Yeah, and their complete tensor structure is then fixed. No? Mm-hmm. It is the stress tensor. No, it is the stress tensor, yeah. Mm-hmm. Uh-huh. Okay. Yeah. Mm-hmm. 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 Right, exactly. So in principle, this could also have, this average dispersion could also have a contribution from a Fermi-Dirac distribution, for example, at the background level. Yeah. Mm-hmm. Yeah. Right, yeah. Right. So, I mean, usually you would think for dark matter that by the time nonlinearities kick in, any sort of primordial value from any initial temperature of dark matter would have decayed like 1/a², while the nonlinear one from shell crossing builds up over time. So this epsilon of z from the shell crossing, we expect it to be a rising function. Mm-hmm. 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 Exactly. So it would decay, and then once you're in the nonlinear regime, you would get this kind of nonlinear contribution to epsilon, which then grows. No? This is the idea. No? Okay, but I should rush through a little bit, I guess. So, okay, for this average dispersion, we have tried actually many different ways to extract it. But maybe I go a little bit, yeah, I need to jump a little bit. So let's see. So this is just some sort of a little bit technicalities, how to set up this whole computation. So basically by writing all the perturbations into a big vector of perturbations, we can bring the equation of motion into the kind of familiar form in Fourier space that you know from sort of standard perturbation theory with a linear evolution matrix and some nonlinear interaction vertices. Just they are now a bit more complicated, so it's some work to determine them. Okay, just flash this, but it's really just fixed by the collisionless Boltzmann equation, right? And at the end, on top of that, you do the usual perturbative solution in terms of the initial density. And the coefficients are going to be kernels, like in SPT, but now the kernels are different, right? So this is basically the difference. And so here, this is kind of an important thing that you can look, for example, at the third order kernel in this typical KQ minus Q configuration and take the limit that Q is much larger than K. So this is this typical UV back reaction term from P13. And of course, in SPT, you get this K square over Q square, K square for momentum conservation, and 1 over Q square just because it's a rational function and dimensional analysis tells you it has to be 1 over Q square. So now in VPT, actually, we also, of course, get the K square. Momentum conservation also happens for collisionless gas. But since there's this additional dimensionful scale of the average dispersion, it can have a more complicated dependence on Q, and it does actually have. And the interesting thing is one can actually understand very easily and simply why asymptotically, if Q is very large, it has to scale with this extra ratio of this K sigma over Q. And the exponent here is basically related to how fast the average dispersion grows. And there's a simple physical picture, which is at some point, basically, you have a sort of dispersion horizon, which grows because the average dispersion grows, so the dispersion scale grows. So a given momentum mode will at some point enter into this dispersion horizon. This is when this K sigma becomes larger than Q. No? And basically, then the mode will stop growing, even at the linear level. No? And so from that point on, it will also not source anymore this back reaction into the very long wavelength mode K. No? So this tells you the higher Q, the smaller the mode, the earlier it enters the dispersion horizon, the earlier it stops growing, the earlier it stops sourcing the large scale mode, the larger is the suppression here in this F3 kernel. And basically the exponent is really fixed just by this exponent, how fast the average dispersion grows. Doesn't depend on the truncation, we checked this, doesn't depend on somehow, some more details of the theory. And so this is basically the UV screening that is now happening here in these kernels, okay? Of course, there's a transition region if Q is not quite as large. And yeah, okay, skip that. So what this basically means is if you plug this into the loop integral is that for arbitrary, I mean, look at a power spectrum, which is kind of a K to the NS with some spectral index, just a power law spectrum to start with. And so usually when NS is above -1, the P13 in SPT is UV divergent. So now with this extra screening, basically the slope of this is kind of the integrand, the blue line is the VPT. This extra UV screening tells you that independently of NS, sort of the higher NS, the faster this average dispersion grows in a scaling universe. You can predict this exponent just related to NS. The stronger is this UV screening, and this compensates kind of the stronger growth of your linear input spectrum, so that in total you always get kind of a UV finite integral nominally. No? So for the scaling universe, actually there is just from scaling symmetry, you know this exponent alpha of epsilon, and this is all you need to predict the slope. Yeah. So just NS basically. Yeah. So the nice thing is that you can do this exercise here actually also not at one loop, but at L loop. I mean, this is just a dimensional argument. So it shows you that all the loops are now going to be with actually the same index here. So all the kind of P1, 5, P17, and so on loops. There are also the kind of stochastic loops, P22, and so on. And so overall, one can show analytically that basically this gives you some finite integrand for all spectral indices that are consistent with hierarchical clustering at all, so between -3 and +4, no? At all loops. Okay, so then maybe I just flash this very briefly. So we tested this with the scaling universes for the spectral indices. There's always 4 choices of the spectral index here with n-body and with kind of the one loop prediction in this VPT. And here we determine the absolute, so the time dependence is fixed here and just one number, basically the ratio of k sigma over k and L is the only free parameter then at the end. And this we basically treat as one free parameter, similar like in the EFT, where we have now one parameter that we match to the n-body. But the difference is, of course, that is only one parameter. So if we go, for example, to the velocity spectra, here we have basically already fixed the parameter. So this would be 0 parameter left, or also, for example, the bispectrum. Or also the vorticity, which also is generated in this theory. And okay, this maybe I skip, but we can discuss if you like. We can match also to the EFT, of course, like any UV theory, you have to be able to match to the EFT, whatever you do, if it's a consistent theory. And this would be a UV completion, but you can always match a UV completion to the EFT, so you get predictions for the Wilson coefficients. Yeah. Yeah, so this is basically the CS square, and these are the 4 one-loop bispectrum counter terms, which, okay, I pasted here in very small, so if you look at the slides, you can identify where they are in the paper. Mm-hmm. Mm-hmm. Sure, because you, no. Mm-hmm. 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 No, the EFT is completely agnostic to the UV. So with the Wilson coefficients of the EFT, you can, I mean, like if there are like little sort of Martians, for example, that have a super like spacecraft and shift around galaxies on small scales, this could be a viable UV model. And so the only change in the EFT would be that kind of there's an extra contribution from this sort of to the Wilson coefficient. But here we kind of assume that it's a collisionless dynamics. And so this is the assumption. Mm. Mm, yeah. Sure. I mean, so I mean yeah. So I mean you can phrase it as tau ij, or here I phrase it as corrections to the kernels, but this is equivalent. So you have basically 4 shape functions for the bispectrum, right? And so we no, I mean you have an infinite set of parameters in the EFT, right? And now in VPT you have basically one free parameter, which is this average dispersion to start with, and then you have the average of the 4th cumulant, of the 6th cumulant, and so on. No? So in principle, this is also an infinite set, but okay, much smaller infinite. And also, I mean, then we can discuss the dependence on the truncation. So it's basically the average of the dispersion, because this sets this k sigma scale, this drives everything. So the average of the 4th cumulant doesn't really play a big role, and in particular doesn't enter at all exactly at this order in the matching coefficient at the k square order. Mm-hmm. Mm. Mm-hmm. Yeah. Mm-hmm. I mean yeah. No. Mm-hmm. No. is exactly the EFT parameters, no? So these are exactly the usual operators, all full set. For example, if you want to go up to the bispectrum, you need 4, no? Zero, no, there, no, I didn't, yeah, no. Yeah. So, okay, I mean, I put it here small because it's not meant to be, I mean, you can read it, but we have, I mean, for the F2 kernel, yes, of course, you get all the coefficients here. So, I mean, we can, any UV model, basically, you can see a given UV completion as a prediction of these Wilson coefficients, right? Mm. No. But why? I mean, no. Mm. Mm. I mean, the EFT, no. Mm. Yeah, symmetry. No. I mean, the only thing that you need is that your, I mean, that in the infrared, your UV completion has the same symmetries as your effective theory, right? So this is the way how you construct the effective theory. Rotation, translation, equivalence principle. No. Mm-hmm. I mean, this is, if you take collisionless matter, this is what it is. Yeah. But for the modes that you integrate out, you don't assume that. Why these assume? Mm. I mean, for yeah. Yeah. Mm. So in a given UV completion, you fix all these values, right? And in the EFT, you would say, I don't know anything about all these values. No? But now, if you have UV completion Vlasov, this will give you one set of Wilson coefficient. If you have UV completion pressureless perfect fluid, which we know is wrong, you would get another set of these coefficients. If you have UV completion, some interacting dark matter model that on small scale has self-interactions, it will give you maybe some slightly different coefficients. So I'm not sure I understand the question. I mean, yeah, maybe we can discuss it later. Yeah. Mm. Mm-hmm. 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 Yeah. No. Mm-hmm. Sure. No. Mm-hmm. 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 Yeah. Mm-hmm. Yes. Mm-hmm. Okay, so this is a little bit intertwined. So we have, I mean, we have the cumulant expansion, right? And we have the perturbative expansion, right? So I mean, once I solve perturbatively, of course, it's perturbation theory. No? So it will always get corrections, and if I get close to the nonlinear scale with my external scale k, I will, of course, need to include 2 loop, 3 loop, and so on as usual. So it's a perturbative prediction, but the prediction from each order in the loop expansion now has also an integration like over this internal loop wave number that you usually take as a cutoff somewhere, right? And so the point is that in SBT, for example, the true loop is extremely cutoff dependent, right? But now in VPT, there is a very strong like power law suppression of the kernel in the UV, so that effectively the loop regulates kind of itself at the nonlinear scale. It just doesn't get any contributions anymore. No? And this is the feature that is kind of different from SPT. So in practice, this means that you should get already a better prediction from just naively computing your loops with these VPT kernels, which is closer to the truth than if you would do it in SPT. So you would only really have small corrections, for example, from effects that even go beyond, for example, baryons and maybe some true non-perturbative effects from these kind of small-scale velocity perturbations. So you would expect that you could use VPT as a starting point plus extra counter terms if you want to do really a precise fit, but then you should get very close priors on these extra counter terms. Nonlinear scale, no. So you cannot, I mean, if you do perturbation theory, you're always limited by the nonlinear scale. So, I mean, you could view it, if you match it on the EFT, you could say it basically predicts you the counter terms, but you can also not match it on the EFT and use just the prediction for sigma ij that just comes out, right? Kind of the full theory prediction, if you like. And do the computation with these VPT kernels. Yeah? So you can either use the VPT kernels, which would be the left-hand side expression, or Taylor expand them if you like, and then at each order in the Taylor expansion, the prefactors will be successively higher order coefficients in the EFT expansion. Mm. Yeah. Mm. Mm. Yeah, I mean, no. Yeah. So yeah, exactly. Yeah. I mean, you can, yeah. No. I mean, you can go back to this Klimontovich equation if you like, and you have the n particle correlation functions that are no. Mm. Then yes, yeah. Mm. No. So the Vlasov equation assumes that basically you have in like each kind of cell that you consider sort of enough dark matter particles that the stochasticity of the number of dark matter particles is irrelevant. But okay, I don't want to keep everyone. Yeah. Sure. This is the whole. Yeah. Mhm. So we don't want to predict like the shell crossing here, yeah? But we want to take into account the fact that there is shell crossing onto the perturbations on large scales. So we are just computing perturbative scales, right? But taking into account that there is this average dispersion that is generated by the very small scale shell crossings. So this is the way how in this setup now, as we are computing, basically the non-perturbative information enters. No? And the impact of the shell crossing onto the large scales. This is what is basically, because once you have this kind of average dispersion, which is very UV dominated, which is an input parameter for the computation. But once you have it, then the perturbations of the dispersion are fixed. And these perturbations of the dispersion mean that at some point also the density perturbations stop to grow. And this basically leads to these kernels that have the screening property compared to SPT. Yes, exactly. No. Mm-hmm. Okay, I don't know. You are the chair. Yeah. Okay. Yeah. So let's see whether I can somehow jump a bit. Okay, so whoop. No. This is the yeah. This is the backup here. Yeah. Okay. So I have all the plots that you may want to see in the backup below, but didn't plan to keep you for that long. Okay. So basically, I mean, for this Vlasov perturbation theory, I want to stress that conceptually, it's actually a very simple idea. No, it's really starting from collisionless matter instead of a perfect fluid and doing perturbation theory on top of that. So there's no kind of magical assumptions or anything. It's really a very simple, straightforward idea that we want to follow here. And the essential new ingredient is this dispersion scale K sigma, basically, that is not present in SPT. And that leads basically to capture like features that are just not present in SPT, right? Like vorticity generation, like the decoupling of UV modes. So we looked at density, velocity spectra, bispectrum, vorticity spectrum. We looked at this in scaling universes in lambda CDM compared to simulations. And also systematically now extended it to be able to treat truncations up to, in principle, arbitrary high order. If you go to third, fourth order cumulant truncation, then you have many modes, and we use the spherical harmonic expansion to capture all of them, inspired from like Uroš parametrization, originally used in the kind of for the ISD, but we can also just use that to parameterize all the possible helicity modes of the cumulant perturbations. The dispersion tensor has scalar vector tensor. Then we get kind of helicity 3, helicity 4 modes, and so on. So we are actually including all of that and checking the stability with respect to the truncation, and find that the second cumulant truncation predicts already the bulk part of everything. And this is because this has already the dispersion scale. This has already the UV screening. And then there are small quantitative corrections from the third cumulant, and starting from the fourth cumulant, and in particular helicity 3 and 4 modes, we see virtually no effect on P delta delta. Okay, that's all. Thanks. Mm-hmm. I mean, so this average dispersion epsilon if you, yeah, I mean, if you want to translate to sort of the EFT language, then this already predicts like the first EFT coefficient, which is the CS square counter term. No? So roughly speaking, you can think of this average dispersion as being kind of sourcing the physical part, let's say, in the collisionless case of the CS square counter term. No? Mm-hmm. Yes. Mm-hmm, mm-hmm, mm-hmm. Um, so it does, of course, also change P22 compared to SPT. So there is also a prediction of how large this change is. Yes. Well, I'm not using it. I mean, this is how sort of, basically, okay, given that there is this average dispersion and I'm allowed to do the split into average plus perturbation, right? Then, no, no. Well, this is just, okay, the average is clear what it is, no? And then we can subtract the average from the full dispersion tensor. This would define what the perturbation is. Mm. Sure. So, um, no, we have, no, I mean, it should be really, I mean, what you should take, okay, so this is a question. So how do you determine this average, right? And so the way how we determine this, or what you say is should be included in this average K sigma value that we, I mean, the way how we determine it. So basically the main point is that the perturbations are scale dependent, right? And so as long as we focus only on the perturbative scales, we do not have to compute these perturbations of sigma ij on the small scales. They will be very complicated, non-perturbative, like the average value, but we are not needing them, right? So, yeah. So the, yeah. Mm-hmm. 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 Yeah. Mm-hmm. Yeah. Mm-hmm. 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 So one thing is, I guess, if you go to the two loop, and I mean, this is what we do in Lambda CDM, basically. I mean, this is an example here. And there the SPT gets really extremely highly UV sensitive, right? And so there is where VPT really makes a big difference. So you kind of, yeah, I mean, you kind of, mhm, mhm. Yeah. Mhm. So this is relevant because the size of these counter terms, right? Their main role is to subtract this unphysical UV dependence of SPT. Mhm. Mm, 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 mm. I mean, yeah. Yeah. Mm. Yeah, yeah, yeah. Oops.
I want to ask a question.